Okay, we'll start now. Good evening. My name is Ranjan Bora, and I am a PhD scholar at IIT Delhi. And I am one of the TA in this course, Biomechanics of Joints and Orthopedic Implants. This course is instructed by Professor Sanjay Gupta from IIT Kharagpur. And I have already taken 6 tutorials on this course for the previous 6 weeks. Now today is the week number 7 of tutorial, and in today's tutorial first I will discuss the assignment problems from week 6. After that I will discuss some concepts related to stress and strain on bones, and I will solve some numerical problems. So I will start. First, I will discuss about the assignment problems from week 6, and this was the first question. The first question was implants facilitate the bone ingrowth on implant surface and stable fixation occur through. This was the first question. So there are 4 options. Now, if we see the options, we can see that porous coated porous coated is one of the options which can fit in this mentioned statement, because porous coated implants facilitate the bone ingrowth, because if there are pores in the implant, then bones can grow through the pores of the implant, and it fastens the bone ingrowth process, gets accelerated because of the pores in the implants. And it also create one extra benefit, which is the stable fixation, because if the bones passes through the pores, then it the bones holds the pores walls of the pores, and there are some bonding which get developed between the walls of the pores and the bones, and because of that the fixation becomes stronger. And you can see from this diagram, like this is a porous coated implant, and you can see this is the porous coating, and the outside is the bone outside layer. So in this figure you can see the bones. These are the bones which gets through to the pores, and because of this because of this branching of the bone, branching from bone tissue, the the bonding becomes stronger. So here option A is the correct. And this process is known as osseointegration. The bone ingrowth and stable fixation, this process is known as osseointegration. Next question, among which of the muscles possess least muscle attachment area in pelvic bone? These are 4 muscle attachment areas in pelvic bone. Now, if we see the anatomy of the pelvic bone, this is the pelvic bone, this is the lateral view, and this is the medial view, and there are various muscles which get attached to the bone. And if we see the anatomy, we can see that the 2, 3, and 4 is there. These muscles are gluteus medius, and iliopsoas. Now you can see this is 11. This 11 is very small, the attachment site, which is the rectus femoris. So among the 4 options, the option D is correct, rectus femoris. Next question, statement is given: partial volume effect can result in the loss of apparent property in FE model because of the limited resolution of the imaging system. So we know that in partial volume effect we lose some property of the model, and in FE model we need the detailed for FE simulation we need the detailed model. So if we lose any resolution in the imaging system, then which is not suitable for FE model. So it is a correct statement. Because of partial volume effect, there is a loss of apparent property in FE model. Next question: who is considered as the father of modern THA? So among the four options, option A is correct. THA is total hip arthroplasty. Sir John Charnley is the father of modern THA. Next question is: the failure scenario arises due to wear particles debris from articulate surface known as. So we know there are different failure scenarios which can get arise uh, in an implant, and if the failure scenario is because of the wear particle debris from articulate surface, then it is, you can see in this figure, this is the implant, and sorry, this is the articulating surface, and this is the implant. So some wear happens in the articulating surface, and this because of that wear, uh, there is bone resorption happening, and this phenomenon is known as particulate reaction, option B. Next question: implant bone interface failure due to debonding. Yes. So we can treat the implant bone interface as a composite material, because you can see if this is a implant, hip implant, and the surrounding bone, this is bone. So these two has different material properties. Like if it has Young's modulus of E1 and the bone has Young's modulus of E2, so we can treat this system as a composite material, and we can use the Hoffman's failure criterion. Here it is showing the equations for Hoffman's failure criterion, and this failure criterion is used for composites. So option A is correct. Next question: the CT attenuation value of soft tissue is approximately. So these are different CT attenuation values for different items. You can see for bone it is 400 to 1000, for soft tissue it is 40 to 83, and for water it is 0. So for soft tissue, option B is correct, 50. Question number 8: major reason for the stress yielding is. So we know stress shielding happens because of the difference which get arises between the difference in the stiffness or Young's modulus between the implant and surrounding bone. So if there is change in stiffness of implant and bone, then we can see the stress shielding phenomenon. So option B is correct. Now stress shielding increases with increase in. So stress shielding happens because of the difference in stiffness of implant and bone. So if we increase the stiffness of implant, then because the stiffness of bone is constant, so if we increase the stiffness of implant, then the difference becomes larger and larger, and because of that, stress shielding increases. So option B is correct. Next question: possible sources of generation of wear particle debris are. So there are four options. Option A is acetabular bearing surface. Option B is abrasion of cement implant oblique bone interfaces. Option C, fretting between metal parts in modular prosthesis. And option D, all of the above. So we can see that because of all the options A, B, and C, there are the generation of wear particle, because these three are all wear phenomenon, types of wear. So option D is correct, all of the above. Next question. The statement is given that the modeling of cartilage layer at articulating surface in FE modeling of pelvis reduce the stress concentration. So we have to say it if it is a true or false statement. So there are some results in the uh, pelvic bone, and means these results are with respect to considering the articulating surface and without considering the means the cartilage layer. So you can see these are the results of von Mises stress distribution in the pelvis cortex, and this is the result which says has a cartilage layer, and it also has a cartilage layer. Here the femoral heads are different. Here it is anatomical and it is spherical. And the third picture, this picture has no cartilage layer and it is spherical femoral head. And you can see if we do not model the cartilage layer, then there is an increase in stress distribution, as you can see this red contours. And from here you can see the red contours means like more stress. So if we do not consider the cartilage layer, then we will get the more stress, higher stress, and because of the higher stress, there are higher stress concentration. So this statement is a correct statement. The modeling of cartilage layer reduce the stress concentration. Next question. Digital image correlation method helps to measure. So we use the digital image correlation method for strain distribution. You can see the all the three options are stress concentration, but we only use for the strain to for the measurement of strain. So option C is correct. Next question is which of the following is not a procedure involved in finite element modeling of bone? So in the previous tutorial, I have discussed about these methods: thresholding, region growing, and these are all the methods are we use for the segmentation purpose. Means for segmenting the different bones from the CT images, and uh, and those are helpful. Like once after doing the segmentation, we create the model of the bone, and that we use that model for our finite element modeling. And contour detection is also there in the segmentation process. So option C is correct, because digital image correlation is a method which we use for the measurement purpose in our experimental study. So here option C is correct. Now next question is linear displacement sensors is used to measure depth of an implanted bone specimen. So from the question you can read it is a displacement sensor. So and displacement sensor means it measures the displacement. So if it measures the displacement, then option C is correct, micromotion, because the remaining two options are strain and strain, and it only measure a micromotion means displacement. So option C is correct. Which technique is generally applied to simulate physiological high compressive loads of the human spine? So we use the follower load technique to simulate the physiological high compressive load. So option B. Next question, what surgery is used to join two or more vertebrae together to prevent motion in the destabilized segments of the spine? So you can see it is a fusion surgery. That means in this you can see this is there are uh, some fractures here, and how do you fix that fracture? We use this implant, and finally we fuse the two vertebrae together. So the option is fusion surgery. Next question, dash and dash are few of the requirements of speckle pattern DIC measurement. So we have few requirements for the speckle pattern DIC measurement. You can see These are the requirements, like it should be non-repetitive and isotropic, high contrast, then only it shows the good speckle pattern. And from the options we can see that option A is correct, non-repetitive and high contrast. Next question, what is the most prevailing failure scenario of cemented hip stem? So the most prevailing failure scenario of cemented hip stem is accumulated damage. Which bony structure within the scapula is not subjected to bending? So this is a scapula, and if you remember from these slides we have discussed previously, can you identify these anatomical sites in the scapula? So scapular spine is here. This is the scapular spine. And acromion is somewhere here. Acromion. And lateral border is this side. This side is the lateral border. And infraspinous fossa is this region, the blue colored region. And this is the result of a simulation of scapula after applying the bending load using finite element analysis. So from this figure you can see this blue means this in the right side you can see the principal stress values, and blue means you can see very less values, zero, almost zero, and means the color is changing from blue to red and the stress values are increasing. So this infra this infraspinous fossa, so this infraspinous fossa has the least stress values which are blue colored. So that's why here option D is correct. Means there will be no stress, zero stress developed if we apply the bending load to scapula. Next question, which of the following is a full field measurement technique? So the full field measurement technique we have studied, it is the digital image correlation. So option A is correct. Okay, now I will discuss some concepts from these slides, and I will solve some numerical problems. So first concept is stress shielding and bone remodeling. So what is stress shielding? We already studied. Like if the implant and bone has a difference in stiffness, then after means uh, after the implant is inserted into the bone, the stress shielding will happen. Stress shielding means there will be some there will be mismatch in the bone, there will be mismatch in stiffness properties of uh, implant and bone, and because of that the load will completely be taken by the implant, and the bone surrounding the implant will not take any load. And because of if the bones doesn't take any load, then there are the phenomenon known as bone resorption. uh, so now I'll discuss. So the implant, weighing considerably stiffer than the native bone, carries the bulk of the load. Carried So before surgery the load was carried by the bone, but after surgery the load is carried by mostly carried by the implant. So this alters the load transfer pattern across the implanted bone, and consequently a significant portion of bone which was exposed to loads in intact condition is shielded from carrying the load by a stiff prosthesis in the implanted condition. And this sudden change in stress strain distribution is known as stress or strain shielding. So you can see this figure, like this is a femur bone and this is a hip implant. So after the implant is inserted into the femur bone, then these surrounding bones, the bones in blue color, they don't take any load because all the loads are taken by this implant. So the uh, the bone surrounding the implant, because of their inactivity, because bones remain active if we only apply the load. If we don't apply any load to our bones, then remains inactive. And if the bones remain inactive, then the bone reabsorption happens. Means there will be reduction in density of bone here. So the surrounding bones become weak, and because of that there will be some implant loosening. Means this implant will be not properly fitted to the patient, so some difficulty after the surgery because of this stress shielding phenomenon. So in this I am giving you an example, like if there is a bone which has a we know the cortical bone has the Young's modulus of almost 20 gigapascal, and if we apply a load of 50 newton, and assuming the cross section of the bone as 10 square, so what will be stress in the bone? So we know the stress is F by A. We have already discussed this. So F is 50, area of cross section is 10, so it will be 5 megapascal. Stress in bone is 5 megapascal. Now this was before surgery, and this condition is after surgery. Because in surgery what we do means we remove some bone and then we insert the implant which has a higher Young's modulus, because these implants are mostly made from titanium or steel, and those metal has Young's modulus of 200, around 200 gigapascal. The steel has This is the Young's modulus for steel. So now um, can you determine the stress in bone and stress in this implant? Stress in bone and stress in implant. Initially it was 5 megapascal. Now after inserting the implant into the bone, what will be the variation in stress distribution? You can see cross section becoming half 5 mm square. So now I will solve that problem. Like if we apply a force of 50 Newton, then what will be the stress in bone and stress in implant? So we know that this bone and implant, they are in intact, means they are in contact. So after applying the force, the this means the deformation will be equal for both the bone and implant in this condition. So if we assume this delta, deformation is delta, so this delta will be same, delta bone will be equal to delta implant. And from the Hooke's law, we know what is delta. Like from the Hooke's law, we have Young's modulus equal to stress by strain. Stress is F by A, strain is delta by L. So delta becomes from here, delta equal to FL by E, FL by EA. So delta bone will be F, I am representing bone as B, FBL. This L is same for both bone and implant. So FBL by EBA, area of cross section is also same, 5 mm square, equal to delta implant will be Fi, implant is I, L by EIA. Okay, we'll first derive a general expression. Like we'll not assume that this area of cross section is same. Like we'll consider for AB and AI and LB and LI. Now from this equation, you can write FB as EB AB by EIAI into FI LI by LB. We'll take this LI equal to LB. So this term will be cancelled out. So this is the FB. Now you can see if it is FB and if it is FI, then it should be FB plus Fi equal to 50, because we are applying 50 Newton force. Now in this expression, if we substitute this expression for FB and if we take Fi common, then Fi will be EB AB by EIAI plus 1 equal to 50. Now if you substitute the values here, EB, EI, AB, AI, what you will get? EB is Young's modulus of bone, which is 20 by 200. AB equal to AI plus 1 equal to 50. From here, Fi will be equal to, this will be 1 by 10. 1 by 10, 0 0.1, 1.1, 50 by 1.1, which will be 45.4 Newton. And from this expression, you will find out FB. FB is 4.54 Newton. So you have found out FB, and Fi. Now you can find out the stress. You can find out the sigma I and sigma B. So sigma I will be Fi by area of I, which is 45.4 divided by 5. 9.08 megapascal, and sigma B, sigma in the bone is Fp by AB, which will be 4.54, it will be 0.9. So you can see the difference, like previously the stress in the bone was 5 megapascal, but after inserting the implant, the stress reduces to 0.9 megapascal, and the stress in the implant is 9.08. So whatever the load is acting 50 Newton, you can see the maximum load is taken by this implant, and the minimum load is taken by the bones. And because of this, because of the differences, the stress shielding will be stress shielding. There will be stress shielding between the bone and the implant. So, and this reduced mechanical stimulus will trigger bone resorption. As I have already mentioned, the bone resorption means the decrease in density of the bone. Now, there might be two cases. Like this expression we have derived from our we have derived in the previous slide, and so what we want this F implant was very high compared to F bone. F implant was 45 and F bone was 4, so it is almost 9 times higher than the force in the surrounding bone. So we want to decrease this F implant force in the implant. So from this expression, if we want to decrease this, what we need to do, we need to increase this. So how we can increase this term, the bracket term in our bracket. So to increase that, we need to increase this because 1 is constant. So how we can increase? Again, this numerator term is constant because we cannot do anything to Young's modulus of bone and the area of cross section of bone. It is already there and we can't do any modification. So the modifications we can do only to the denominator term. The either we can reduce the Young's modulus or we can reduce the area of cross section of implant. So if we reduce the denominator term, then this term will increase, and so ultimately this term will increase and this force in the implant will be reduced. So how we can increase? So if we reduce the Young's modulus of the implant, then it is known as the porous implant. And in case 2, so after doing that, F implant will keep on decreasing. Or in the second case, what we can do, we can reduce the cross-sectional area of the implant. So again, if we reduce this cross-sectional area, then this term will be increased and F implant will be decreased. So because of the stress yielding, we get these problems like bone resorption. And the solution is we use the isoelastic material, means the material which has the same properties as bone. We use that material in our implant. Next, I will solve some problems related to failures in bone and stress and strain. So this is the first problem. It is a hypothetical uniaxial compression test was performed on a machined cylinder of human femoral cortical bone of 6 mm diameter, and the results of the force displacement measurements are shown in figure. Estimate the elastic modulus and the ultimate strength of this sample of bone. Now force displacement diagram is given. This is the compression test and this is a sample of human femoral bone. This F is acting on the bone and it is a compressive load. So how we can solve this problem? So we are given with the force displacement diagram, and using this force displacement diagram we can generate the stress and strain diagram. And in the question we need to evaluate the elastic modulus and ultimate strength, and we know what is the elastic modulus. Elastic modulus is nothing but the slope of this linear segment of stress strain plot. So we need to determine the slope from this plot, and the ultimate strength is the maximum stress a material can withstand, that is known as the ultimate strength. So this force displacement diagram we need to convert to uh, stress and strain diagram. So from this diagram you can see this linear portion and This is 0.09 displacement, and corresponding to this the force will be 3500, around 3500 Newton. So for this point, what we can do, we can find out the stress and strain. Like for this point, the stress will be F by A, which will be 3500. Bone is means the cross section is circular cross section with 6 diameter. So area will be pi by 4 d square, 6 square. So if we calculate, it is 123.7 megapascal. And corresponding to this point, the strain is change in length divided by original length. So change in length is 0.09, and the original length was 12 so it will be 0.0075. Now the elastic modulus or Young's modulus, it is E equal to stress by strain. Stress we have calculated 123.7, and strain is 0.0075. So if we do this, so it is coming as 16.49 gigapascal. So we have found the Young's modulus or elastic modulus. Next, we need to find the ultimate strength, and to find the ultimate strength, we need the mean stress corresponding to this point is the ultimate strength. So it is around 5400 Newton. So because if it is a stress strain plot, then this maximum stress and strain, the point at which the stress is maximum, that point is known as ultimate strength of the material. So, and from that diagram means ultimate strength will be, this force is around 5400 Newton, and area of cross section is pi by 4 6 square, and it will come 190.98 megapascal. So this was the first problem. Now I will move to another concept regarding the testing of bone in bending. So like in the laboratory, how do you evaluate the mechanical properties of the bone, like like its excuse me, like its elastic modulus, then failure strength, ultimate strength, failure strength in compression, then bending, then torsion. So we do some bending test. Like you can see, figure A is the 3-point bending test, and figure B is 4-point bending test. And you can see a force F is acting here, and it is simply supported at these 2 points. And because of this force F, the reaction forces will be F by 2 at these 2 points. And these are the shear force and bending moment diagram. Like this is 0, then this is in positive direction, so it is F by 2. At this point F is acting in the negative direction, so it is getting decreased by F, then again, so it is minus F by 2 at this point. And this is a bending moment diagram. At this point the bending moment is 0, and it is at this point at the midpoint, that means at the point where the force F is acting, the bending moment is maximum. And this magnitude of this maximum bending moment is FL by 4. How it is coming as FL by 4? So if we consider this point, um, and means the maximum bending moment point, at this point how do you calculate the bending moment? Bending moment will be F by 2 multiplied by L by 2, so it will be FL by 4. So using this testing, we can find out what is the maximum applied force F we can act on the bone without getting any failure. And similarly, in the 4-point bending test, we apply force F at 2 points in the bone, and the bone is simply supported at these 2 points. And again, this is the shear force and bending moment diagram. Here the maximum bending moment is Fa by 4. Now there are some assumptions for the testing of whole bone. These assumptions are: the sample is straight, unstressed, and with uniform cross section, and the material should be isotropic, linear, elastic, and homogeneous material. Uh, and the length to width ratio of 20:1 is recommended, otherwise shear force dominates. And means these are the samples which we can generate, or which can generate produce in our laboratory, like the samples with similar mechanical properties with our bone. Sorry, the bone is anisotropic, so we do the testing in a sample, and we assume some material property, like the material property of the sample should be isotropic, linear, elastic, and homogeneous material. And this length to width ratio is 20:1 is recommended, and crushing of loading points must be avoided. Now there is a problem related to testing of bone. The problem is a force of 4000 Newton acts at a distance 60 mm from the axis of the structure, where we consider idealized bone cross-sectional area as illustrative. Determine the moment of inertia and the maximum bending stress. The inner and outer radii for bone section are given Ri 20 and R 0 25 mm. So this is the section of the bone, and force F 4000 Newton. So force P equal to 4000 Newton and acting at a distance of 60 mm means this is P, and if we consider this as our axis, then this distance is 60 mm. So so what will be the bending moment? Bending moment will be 4000 into 60 will be 24 into 10 to the power 10 to the power 4 Newton mm. So this is the bending moment. Now for this section, what is the formula for moment of inertia? We know for a circular section of radius r, the moment of inertia is pi by 4 r to the power 4. So this section, and for this section, like we have two sections here, one is small r and one is capital R. So what will be the combined moment of inertia? It will be pi by 4 r naught to the power 4 minus ri to the power 4, and 25 equal to 181 132 mm to the power 4. So we have determined the moment of inertia. Now what we need to determine? We need to determine the maximum bending stress. So how we determine the maximum bending stress? There is one relation in bending. If this is a shaft and we apply a bending moment M, and this shaft has a moment of inertia I, then and we know, means there is one relation which is m by I sigma b by y. So what is y? So if we assume this cross section, and in bending moment it is known as the neutral axis. Neutral axis means at this axis the bending stress is 0, sigma b is 0 at this axis, and it gets means it gets increased. This is y, this coordinate is y. So this is the stress distribution. uh, Sorry, this is distribution for magnitude. Yeah, the stress distribution we can see from here. Means it is like this. The portion above the neutral axis, it is getting a tensile load, and portion below the neutral axis, it is getting a compressive load. These are the magnitudes in a cross section. This is not representing the direction of stress. The direction of stress is given in here in this figure. So we see that the stress is maximum at the periphery, outer periphery of the bone. So what is y here? Y will be the outer radius. Y will be r naught, and we need to find out sigma b. So we are taking y is equal to r naught because in the question it is asking the maximum bending stress. It is my by I m r naught. What was m was 24 into 10 power 4. R naught was 25. I was 181132. 181132. So it will be 33.12 megapascal. How do you got this megapascal unit? The unit for m was Newton mm, and r naught is mm. I unit was mm to the power 4. So it will come as Newton per mm square. Newton per mm square is megapascal. I hope it is clear to you. Next we will take one more problem. This problem involves bending and twisting and also the compressive load in a bone. So the question is, femoral diaphysis is idealized as a circular cylinder with a periosteal diameter of 3 cm and an endosteal diameter of 1.2 cm. calculate the diaphyseal failure load for uniaxial compression and the failure moments for bending and torsion. So these are given to us. The failure stress values are given to us. This is failure stress for compression, C is for compression. This is failure stress for shear compression, and this is failure stress for bending. Now the femoral length is given as 42 centimeter, and the femur is simply supported. So how we'll do it? Like the compression load is given as 195 megapascal. Sigma C FC, and what is sigma FC? Sigma FC will be F by area. F in compression. This is FC we need to find out. In the question it is asking what will be the FC, means the load in compression such that the bone gets failed by compression. So FC will be 195 into what is area of cross section. Area of cross section is pi by 4. Diameter is given. Periosteal diameter is 3n, the endosteal diameter is 1.2. So radius will be 1.5 and 0.6. Pi by 4. Okay, pi by 4, 3 square minus 1.2 square. It will be 1157.8 Newton. Okay, so next we will find out in bending, like failure stress in bending is given 208 megapascal. So like the expression which we derived earlier, sigma bending is m into I by y, and here what is the bending moment? Bending moment, we need to consider the maximum bending moment because it is talking about the failure. So failure will only happen if the applied bending moment is maximum. And from the three-point testing, like we have seen earlier, what was the bending moment? Bending moment is FL by 4. So we'll use this expression. M is F, length is given, femoral length 42 centimeter. We'll convert it into mm, 420 mm. by y is this, you can see, means the radius of the periosteal diameter will be 1.5, so y is 1.5, again it is in centimeter, we will take 150 mm. So this is m. Wait, sorry, this is bending moment expression was FL by 4, so 4 will come here, it will be 105F. And what is moment of inertia? Moment of inertia will be pi by 4 r naught to the power 4 minus I to the power 4, which will be pi by 4 into r naught is 1.5 centimeter, 0.6, 15 mm minus 6 to be 148.4, sorry, it will be 4, so this 38742.9 mm to the power 4. Now if we use this expression, sigma b is mi by y, from here what we can find out? We can find out m. M will be sigma b y divided by I. Sigma b in failure it is given sigma fb 208, and y is this is y, so 3 1.5 15, and I is 38742.9, so it will be 208 into 15, 0.08. think it is in Newton. Okay, I'm sorry, I have written this expression. This my by I. So mm, n will be sigma b I divided by y should be 208 into I 387 y is 3 centimeter 115. So m is is 5 3 7 2 3 4.8. Now if you use this expression m equal to 105 f, from here f will be 5116.5 Newton. So means this f is for bending. Like if this is our bone sample, then we can apply a maximum force of this fb, uh, maximum force of this fb, such that the material doesn't get failed. If we apply a force higher than this value, then there will be failure in the material. So, or if we apply an force equivalent to this value, then also there will be some failure. So we should apply force which will be less than this fb. Next, in the question it is asking about the failure moments for bending and torsion. Okay, so it is asking the moment. So moment is fl by 4, yes, or it is 105 f, which we have already calculated, Newton mm. Now for the torsion case, we have given the maximum shear stress 69 megapascal. So what is the torsion equation? We have T by J equal to tau by R. Here R is the radius of cross section and tau is the shear stress. T is torque or twisting moment, and J is the polar moment of inertia. J is polar moment of inertia. T is twisting moment. Tau is shear stress, and R is the radius. So we can see from this tau is Tr by J. So how does tau is related with R? Means if we consider this as our cross section, then at this point tau is 0 and tau is increased. Again, this is a magnitude diagram, means this arrows represents the magnitude of shear stress. It is 0 here, and at the periphery the shear stress magnitude is maximum. So we need to consider the maximum shear stress. The maximum shear stress is given the failure stress. We need to consider the maximum radius, means at the periphery, and using that we need to find out the torque or the twisting moment. An expression for J for a circular section is pi by 2 r to the power 4. So in the question tau is given 69, so it is 69 equal to, we don't know the twisting moment. Radius is r is radius of the outer cylinder, which is a diameter of 3, so radius will be 1.5, it will be 15, and J will be overall J, which will be pi by 2, 15 to the power 4 minus 6 to the power 4, so it will be 15 7 7 4 8 5 and 8. From this T will be into 69 T will be 69 into equal to 3 5 6 4 3 4 and 7 Newton mm. So this is the twisting moment corresponding to the maximum failure stress in shear. The maximum failure stress in shear is given 69 megapascal, and corresponding to this failure stress, the maximum twisting moment that we can apply is this amount, 356 Newton meter, 356.4 Newton meter. Okay, that was all for today. This video will be available on my YouTube channel, and the link will be provided on the problem solving sessions on the left side of the NPTEL website. From there you can access. And if you have any doubt, then you can post your queries on the Q&A section in the NPTEL portal. Thank you.